Well, hello, everyone. Excuse me. My name is Dan Stansel. I'm head of the Department of Electrical and Computer Engineering at North Carolina State, and I'm also lead the IBM Quantum Hub at NC State. I really enjoyed the presentations from the panelists, and I know that it was a tight schedule and there wasn't perhaps time to have all the questions that you might have or would like to direct towards the panel, or perhaps even to each other. I think that it's quite likely that that there are departments who are attending who also have experience in implementing our quantum programs who would have some ideas to share. Maybe to just to kick it off, while we give a chance for people to present questions either to the any of the panelists or to each other, is I'd maybe like to ask just the panelists, and each of them could respond if you would like. There's been some discussion about curriculum and courses at various levels, and some universities already have some things in place, and it seems like there is a sort of a low-hanging fruit approach that might have to do with some minor certificates, concentrations that might all be within ECE, let's say. And then there is a multidisciplinary quantum engineering, which perhaps could be at a graduate level or not. And I'm just wondering if you have any comments about where's a good place to start? If somebody wanted to do something, what is your sense of the trade-off between doing something entirely within ECE and then trying to do a multidisciplinary activity across the university?
I guess I can go first. I'm all for the low-hanging fruit because I think it's kind of a good way to kind of test the waters, like start with something small before you commit to something massive. But then, yeah, I'm a software engineer. It shows.
At UMD, we are doing it not all in ECE. To begin, it's ECE physics, computer science, material science may also get involved. And that sounds like it's not low-hanging fruit, but let me suggest why it could be easier. If you have a core of faculty that goes across departments that wants to develop such an educational program, having it across departments, if approved up high by deans, can push back against the zero-sum game politics that also often exists within a given department, and can squash any new thing where there's demands, understandably, in a quasi zero-sum game that maybe we're all used to within departments. It also is, it may be less threatening if it's not core within a department, it's to others who aren't in this field. Sorry to speak so bluntly about things, but there is a trade-offs that exist. But I think a key is a core group of faculty who can do the job, the educational job, and want to do the job.
Joe or Celia, anybody else like to chime in?
Yeah, sure, I was just thinking about the statements that Ronald was making. So I think a lot of it depends on the kind of whether or not there's a quorum of people within a department who can teach it. You don't really want people learning the material to teach the course, at least the first time, because then you'll get something pretty shallow. So like at a place like UMass Amherst, where we really don't have the head count to teach it all within ECE, it would have to be across departments. And I imagine there are a lot of places, whereas it's somewhere like Maryland, where there's, a large quantum population, or MIT or somewhere like that, it makes sense to keep it all within a department. So I think it really, if you want to do it all with it, you know, it's really a matter of time scale with which you could implement such a program a lot, you know, to a large extent, whether or not I think you want to do it both, and whether, you know, and content wise, I think that one of the big challenges with quantum engineering is the diversity of topics that you have to learn. Like in our computer engineering program, we keep pulling away physics and electrical engineering from the program. But in a quantum program, you know, you can teach it all at the like algorithmic level, but in an electrical engineering department, I would think we'd want to get into the kind of device physicsy stuff. But then you also have the kind of information theory, and so there's a broad set of skills in the programming. I mean, you need to learn like what complexity theory is and so forth to really understand quantum computing. So I think there's such a broad range of skills that you can teach that it's hard to constrain it to one department, in my opinion, unless you want to, you know, step on other departments' toes in terms of what you're teaching.
Yeah, thanks for those great thoughts. I see that Truong Nguyen has put a question in the chat. Maria presented a slide on the number of jobs available in quantum computing engineering. Number of jobs is in the range 500 in 2019, which is still quite small. Please comment on the job prospects in the next few years. And I might just maybe to add a little footnote onto Truong's question. And I know that there was scatter in your chart, Maria, but it looked like it was flattening off right at the end. Is there any significance to that?
I will admit I borrowed that chart from a paper. I didn't keep track of jobs at those points, so I can share the aggregate website from which they took this data. It collects job postings from different companies that both, basically from all three kinds of companies I talked about, companies that specialize only on quantum computing, that have a big investment in quantum computing, and those that are just looking to figure out whether quantum computing fits. So you can keep track of it if you're interested. You can take a look. I cannot comment on whether it is flattening out or not, just because I don't have this data, and I try not to comment on things without data. But at this point, yeah, I agree that the job market in quantum computing is much smaller than in established, like general software engineering or other kind of non-software engineering jobs. It's still an emerging technology. It's still in its very early days, comparable to where classical computing was 70 years ago. There was not a market for software engineers at that point too. So we are cautiously optimistic that it will grow, but it's not going to be as broadly spread as other kinds of engineering in the next 5 years.
Perhaps Celia from QEDC would have actual numbers. Speaking anecdotally, I am peppered regularly by entities large and small looking to hire people in quantum technologies, not just computing, materials, sensing, etc. And as I commented in the chat on the prime and the core discussion, the salaries they're offering are often very large. And some of my former students getting, you know, $200,000-300,000 a year job offers right out of grad school, and multiple offers. Okay, so whatever the actual numbers are, that implies strongly that the ratio of candidates to job offers or job openings is favorable to the candidates right now. And again, not just computing. Some of the big tech and other big traditional companies have major efforts going. They're may not be super well known publicly because they're still kind of in the skunkworks mode, but in developing all sorts of sensing tools for a wide range of applications. And this is true in Europe as well. When I communicate with Europeans over there, big companies, the Bosches and Daimlers and things like this have a lot of things going in that area too. So again,
Yeah,
that's anecdotal.
No, thanks, Ron. That's great. I see YC Wang has also asked a question about, transfer. Can things that you learn in quantum engineering be translated to other EE jobs? And maybe I'll toss that one over to Joe. I think that you sort of made some points in your presentation about how there are many parts of a quantum computing system, at least that use concepts that are used in other contexts in electrical and computer engineering.
Yeah, I mean, so certainly there's a lot of engineering that is going into developing the next generation systems, ranging from IC design to mechanical engineering. So I would say that certainly in the same way that a job at, say, JPL leads to work that can, transition to other places quite easily, quantum computing gives kind of requires a diverse set of electrical engineering skills. So I think that, you're not going to transition from architecting a quantum computer to architecting Intel's next processor. But I think that in general, the quantum computing positions, at least the ones I've seen filled, are mostly filled with PhDs who have kind of a mixed background of picking up electrical engineering skills and learning how to program FPGAs and other things that you could transition elsewhere with. I don't know. I don't want to comment how hard a transition would be just because I have no experience shepherding someone through such a transition, but I know people transition from other fields to quantum computing all the time. So I imagine you can transition back.
Well, Joe, I'm following up on that a little bit. You wrote a great article in the Microwave magazine for microwave engineers not too long ago, and one of the things that it seems to me is that a lot of the concepts in a microwave engineering program would be taught, let's say, in the context of a communication system or radio, but in many cases you could use the application as a quantum computer to motivate the different system blocks and concepts as well. Am I?
Yeah, you're absolutely right. And in fact, a large reason why at least the superconducting quantum computing community is where they are is the 4G revolution, where you got commodity signal sources and so forth. And so the hardware is very similar to what you'd see in a communication system with some subtle differences. And either from a course educational position, you could use it as examples, as you suggested, a microwave course, or from an industrial perspective, you can either hire people with experience in things like cell phone design for that particular control, or Keysight has experience in generating waveforms, and they can apply their expertise, and there are many other companies looking into things like that. So there's a lot of synergy between the technology that's been developed for this wide scale commercial applications and kind of the emergence of the quantum computing technology. I mean, those racks I showed in the presentation at Google are just full of signal generators, FPGAs, and high-speed digital to analog converters and then up converters. So it's technology that is well understood from the microwave community. And so yeah, there's it's not a completely different field in that sense, in that there's a lot of overlap.
Absolutely. Like the people who build, debug, and make operate an NMR machine or an MRI machine, as one example, is very similar to what you're doing in certain aspects of quantum computing. The pulse sequences, et cetera. There's a major fundamental physics difference, which makes a difference between just getting out information about spectra or imaging and doing a quantum computer, which is that you're not initializing the spin states, right? And so that's a fundamental difference, but in terms of the engineering aspects of what you have to do in terms of the pulse sequences, the RF control, magnetic field control, heat management, all these kinds of issues, materials issues, mechanical issues, it's very similar. That's just one example.
I see Truong was also asked about system level thinking and what's the best way of doing that? Projects, hands-on internships, any thoughts from the panel or anyone else on that?
Probably in the early days, maybe forever. I see what Maria and Joe and others think. Some form of hands-on training that will in the early days be working on capstone projects, internships in labs, whether academic or nearby industrial or government labs, something like that, where somebody can have a bit of a soup to nuts from conception to realization and debugging project that's quantum in some way, I think might be the best experience. I'm working myself on trying to develop what will hopefully become hands-on advanced laboratory courses in quantum engineering, different from advanced lab courses in something like physics, which I've done before, but it's going to take time and be very expensive to get that going. In the interim, we've got to train people, I think, in some sort of hands-on activity. Hands-on could be on the keyboard, but you know what I mean, sort of practical project-based training, I think.
Yeah, I would agree with that. Internships are great. They're, of course, limited. So I think some sort of exposure to, you know, for quantum control, for instance, some exposure to how qubits respond to waveforms and so forth. There's a kind of counterintuitive aspect of this whole thing, that you have kind of continuous control but discrete measurement, and that's something that I think is really well handled by experiment. And you could potentially make like software emulators and so forth. And I mean, they exist, but you know, poking around and things is a really good way to learn. I agree, it's hard to do it in a university setting, at least at the current cost scale. If there were a way to get that down so that it could be more widely spread, it would be really helpful. And you know, that might be very interesting for, you know, NSF or something to explore.
That's why I'm lobbying for the NSF to fund it, and maybe regional centers. I'm repeating myself from my presentation, just as to be practical.
Yeah, this is true. I asked a question. So I think it's a way for the companies or the research lab, national lab that have the equipment or the devices to get together and offer some internship. I think if that happens, then you'll be able to create your own pipeline, right? I mean, still need to be able to know what's going on before they get to the field. So maybe between sophomore and junior is when they're starting to think about their concentrations, right? Having some kind of internship, you know, maybe 10 to 20 across the US. That would be very useful to create your own pipeline. Otherwise, it's very hard to find, without the jobs, very hard to create, you know, the student who might be doing an MS in the area.
I agree. There's another follow-up question to yours from Wei Lee. And I think what you're suggesting addresses that question also, that point, to some degree, if you can see it on the chat. Coordinating this in an effective ways, of course, we can't just all, we have to take action ourselves in our individual universities and departments, but I'm calling to the degree that there are NSF and NIST people listening for NIST with QEDC. It's the resourcing of this kind of thing I think they need to do, and I would suggest not in a competitive way, not in a way, again, that picks certain places won the award and get to help the students. I think they have to do it comprehensively in some way, so every place is going to get resourced to do it.
I appreciate that point, Ron. And Maria, I appreciate your your comment in the chat also, and makes me think this may be the direction that you're thinking, but exciting applications can generate student interest in a topic, and then if they discover that topic has other applications, then you certainly win in terms of motivating them as well as using a useful skill. But I think these are all great points and great questions.
So I have one additional piece of feedback to this undergrad and the curriculum, is that kind of last couple of years is really the beginning of the company, companies really having growth. I mean, IBM's been big for a while, but Amazon, Google are growing extremely fast. There are other teams growing, and because of the kind of limited resourcing with the smaller teams, it's mostly been PhDs as far as I can tell. And I'm sure back when, Bell Labs was working on transistors and so forth, there weren't a lot of jobs for undergrads there as well. But as things start scaling towards bigger instruments, bigger systems, I'm sure that there will be more opportunities for more entry-level positions. So it's kind of hard to have a crystal ball to know exactly when that'll happen, but I would imagine it's going to turn more, and people can have more narrow roles on the teams and so forth, and not be so focused, essentially the head count being less critical to the overall projects as they grow bigger. So I'm not sure it's possible to make the prediction like, yeah, it's a hard one because, we don't know what's going to happen 5 years from now.
Yeah, the way I tend to think about this a little bit, and you guys tell me if I'm really off the mark, is I took a course, and when I was an undergraduate, it was a very long time ago. So I'm acutely aware that it may not be representative, but I don't think it was so uncommon, and it's still not today, take an undergraduate course in electrical and computer engineering where you learn about the physics of transistors and that sort of thing. And a person with a bachelor's degree is not going to take that knowledge and go out and start doing research at Intel or something on how to do fab device process improvement or whatever, or device innovation. But it's a first step, right? That then could get you excited, lead you to further studies and further applications. And for somebody to want to study it in grad school and get a PhD, they kind of have to be excited about it. They have to get a hook early that this is something that might be interesting. I don't know. Let me ask maybe if there are people here in the session who have quantum courses, quantum engineering courses, or have been growing a quantum engineering research program in your department or your university, sort of what the challenges for you have been, or what your experience and what have your challenges been.
You mean not the panel, right?
Not the panel. Yeah, I was curious, if we definitely I'm interested in the panel also, but I was curious to see, if there might be some other interesting experiences just in the group. Well, there might be certainly, if feel free to chime in, stick something in the chat or raise your hand, and that would be great too. But in the same spirit of what are the job opportunities, there has been, Ron referred to a lot of the federal programs, and Celia did also, and we've all read in the paper lots of things that are being considered, federal programs that could impact the National Science Foundation, other government agencies related to quantum. Dominique, could I ask you maybe to just take a couple of minutes and kind of give a sense of the landscape from your perspective? You know, where are we? What's real? What's not real? Are we going to expect to see significant new funding, and those crystal ball kinds of questions?
I wish I had one. Well, you all know, and I think the presenter made it very clear that there's been the past few years quite a bit of excitement and increase in funding in the area of quantum information science and engineering. And in the US in particular, all government agencies have seen an uptick in this area of funding, be it funding internal research for national labs or funding academia. In the case of NSF, for example, and funding teams from DOE and DOD as well. The Initiative Act, a very strong push and support to have collaboration between agencies, and that is supported by the OSTP. So we have multiple working groups that are trying to ensure that the agencies are doing, and we collaborate with each other, so we don't fund the same people, and we increase diversity in the funding, both in terms of the institutions, but also the topics and the ideas that are coming to us. In the specific case of NSF, we have been funding quantum information science at the fundamental level for decades. And we did have some 3 years ago, as part of the big ideas, this program that we call the Quantum Leap, one of the 10 big ideas that had a specific fund to fund new ideas, mostly cross-disciplinary ideas, to try and push the community to start working as teams in the area of quantum information. And that is culminating last year with 3 new, what we call quantum institutes. This year, competition is ongoing, and we should have some more announcements soon about some new centers. That was one area that we thought was very important. Those quantum institutes are multidisciplinary. So contrary to other centers that were more traditionally funded by NSF, like Physics Frontiers, that have some very good research area of physics and material science, the quantum institutes are cross-disciplinary. So the intent is to have people working across different departments, really get the science more towards a future application, or at least some use cases being considered. We also have currently looked and have a competition ongoing on quantum interconnect, which was also mentioned by speakers here, as a means to scale up some of the capabilities that are existing today, which is quite a challenge that needs to be addressed. And in addition to that, you may have heard the words of the street that there is a proposal out for next fiscal years, and it's a proposal right now for entirely new directorate at NSF that would focus on technology. Exactly what it will do is to be defined, but the intent, if it does get implemented, is to push the research towards more translation, innovation, and partnerships. And it most likely would include the convergence acceleration And in the case of quantum, that would mean further partnership with industry, between academia and the private sector, to really move some of those beautiful demonstrations in the labs that we've seen towards something that is more accessible, that is more scalable, that is more practical, and that is hopefully user-friendly at some point. So it does not require entire labs of students tweeting with each other to find out how to reorganize the different modules and controls to ensure that they can do their measurements. So a lot of that is definitely engineering focused, and that's where I think it's going to be very important for the engineering community, if they are interested in moving the quantum information science further towards applications, to actually provide the support that is needed to come up with demonstrations that will ensure that the area of quantum information science and engineering will continue to be funded in the future, because the only way for all those projects to move forward is to continue getting funds, right? And if agencies can come up with breakthroughs that have potential societal impact, like the atomic clock has been shown as an amazing feat of engineering, the MRI is another one. I think those are the kinds of breakthroughs that we need to see from the community to ensure that research is continued, and funding in the area of quantum is going to be a long-term funding, because there's still some fundamental questions that need to be answered in parallel to essentially making systems that are practical. And welcome questions.
Thanks, Dominique. And I see it's 2 o'clock, and I have not been briefed about whether we would suddenly disappear. 5 minutes remaining. Okay, that was the cue. So 5 minutes. I think maybe a way to one way to sort of end on a thought that might be useful is, I think we've sort of touched on the answer to this question, but let's suppose there is someone, a department head, department chair, who's thinking we probably ought to think about introducing a course at some level in our department that's related to quantum engineering. What's the best way to go about that? Any thoughts from the panel? What level, topic? How, Joe, or I think someone may have suggested. No, I guess it was Maria suggested that maybe getting an adjunct to teach a course could be a good approach.
Yes, that's the scenario for university departments that doesn't have somebody who is already familiar with the topic and is comfortable enough teaching it. They certainly can invite a guest lecturer.
The country is large, of course, and not every university or college will be in close proximity to experts. Some will be. Folks in the Northwest have wonderful people like Maria and others. So I would encourage, again, the NSF maybe to make it possible through perhaps the QLCIs or other mechanisms to provide expertise in an adjunct way to diverse communities, all communities in higher education, in a kind of adjunct way, that's not an extra burden on anyone, but somehow a resource to make it positive as an entry point for the colleges and universities who'd like to get started in this area. Again, I think there's probably a lot of goodwill amongst everyone to help each other, but we need to be resourced, and most colleges and universities, except if they're extremely wealthy private universities, are strapped for the resources to do what we want to do in education and helping our colleagues. So I'd hope if there are these large sums that are going to come to the government agencies, particularly NSF, that in addition to helping technology translation to industry, super important, that we also look at the full stack from training at the earliest levels, including the places which do not have the resources now to do anything. A full stack, right? And that's got to somehow be available I'll repeat what I said before, in a somewhat non-competitive way. We can't just have winners getting this. We got to make sure everyone gets access. It's like a public resource.
And actually, our curriculum partners, speaking about software only, had quite a lot of success bringing in quantum computing, quantum software-based courses from scratch, basically without having deep expertise in those universities themselves. So having a kind of package with curriculum materials, programming assignments, guidelines on how to use it can be very valuable, and it might not require like massive financial investments. So basically, we're not asking people to bring in an actual quantum computer into their universities. That would be just not accessible to almost anybody. But having an introductory level course with the materials, with the resources that are available online for free or for cheap is quite doable, and we saw a fair amount of success there.
So Magnus Egerstedt here. I have swung by to, first of all, I hope this session was compelling and exciting. I personally spent time on the other one because it's closer to who I am, but I have learned that people enjoyed this session very much. So thank you for that. And I'm also here to close down the session. So I would like to thank all the panelists for participating in day one, and I hope to see all of you there again tomorrow at 10 a.m. Central Time. So with that, I mean, you can linger if you want, but day one is officially over. So have a great rest of the day in cyberspace.